Okay, friends, I'd like to start off by thanking the organizers. I mean, they've been doing a marvelous job of keeping this meeting going for the last decade or so. And it's really a lovely occasion for the StatMech community to get together and interact. I'm going to talk about a subject that we've had some recent interest in, and that is active matter with quenched disorder. We've all sort of been energized into active matter by, well, primarily the efforts of Sri Ram, I guess, right? So let me sort of give you my 2 bits. This is work in progress, so inputs are very welcome, and I mean, ideas are sort of very welcome. Okay, so here's an overview of my talk. I'll start off with an introduction. All of these will be very short, of course. I'll then talk about the Vic-Check model with disorder. The disorder will be in the form of obstacles which the particles bounce off, basically. That's what's going to be the disorder. I'll then quickly show you some results and finally end with the conclusion. Okay, so here's an overview of this talk. I think here's an introduction. You've all seen the Vic-Check model. That's going to be the basic sort of starting point of our calculation. The usual picture you see is a flock of birds. And the model is for an update of the position field of the birds or active particles and the angle field. And the angle field sort of parallelizes depending on its neighborhood. So this neighborhood is depicted out here, and that has some length scale capital R, say. And then, of course, there's some randomization, which sort of is the noise, basically. Okay. So the control parameters in the Vic-Check model are the density of the particles and the noise strength, eta. And typically you look at the order parameter, which is the average velocity of the particles. At high noise, you have, so here's a plot of the order parameter versus the noise amplitude. At high noise, you have zero velocity. Birds are all flying randomly in different directions. At small noise and at zero noise in particular, you have a perfectly ordered state where all the birds are flying in the same direction, basically. Okay, so that's a beautiful phase transition. And of course, what's remarkable is that these active arrows in 2D show long-range order as opposed to passive arrows. Okay, so just for sort of completeness, I've shown you the eta equal to 0 state. That's a noise-free state. All the sort of arrows are pointing, all the velocity fields are pointing in the same direction. And here's a somewhat higher amplitude. On the average, there's still an order parameter, but there's some randomness in the system. Okay, and this is the well-known Vic-Check model, which all of you have seen multiple times. Okay, so the model we're looking at is the Vic-Check model with obstacles, and this is something I've been doing with my student Pradeep Yadav. Martin Wiegel at Chemnitz, he's an expert on disordered spin models, and myself, and we're actually sort of pondering about when to start writing this piece of work up. Okay, so the model is basically the following. That's your sort of system. The arrows are the sort of self-propelled particles, and you have these scatterers in here, which are sort of randomly located in the system, basically. Okay, so how do you scatter off these scatterers? We consider a very simple rule. You have an elastic scattering. So if you sort of come in out here, you sort of, the radial component is reflected and the normal component stays the same, okay? Just the standard elastic interaction rule. There's a length scale of this also, of the scatterer. And for simplicity, I choose the scatterer length scale, the size of the scatterer, to be the same as the range of the Vic-Check model interaction, okay? The physics does depend on the size of the scatterer, as you can imagine, okay? So what are the control parameters we have in the system? Of course, earlier you had the density, so I'm going to show you results for 0.5 density, whatever. There's a noise amplitude, which I'm going to vary, and there's now an obstacle packing fraction, and that's denoted as phi 0, so that's a new parameter in the problem. As I said, I've set the size of the obstacles to be sort of equal to the Vic-Check model range. And phi 0 equal to 0 recovers the normal Vic-Check model. Okay, so the first thing we did was look at the sort of counterpart of the Vic-Check model order parameter. So here's a plot of the order parameter as a function of noise at different values of the density of the obstacles. So that's the obstacle density 0. That's just the regular Vic-Check model. You already know what happens there. It goes from a maximum at 0 noise down to 0 at some phase transition point. And we now know that this is, I think, a second order phase transition if you use that language, basically. What happens with disorder is actually, with this kind of disorder is rather non-trivial. What happens is the following. So let's look at a typical amplitude of disorder, say 0.04. You have a small peak at eta equal to 0. You come down to a minimum and you rise the maximum as is at non-zero noise, as a matter of fact, and then you sort of come back down to 0 again. Okay, so I mean, we didn't see any obvious way of explaining this, so we sort of studied various movies, etc., of the Vichek model with disorder, and let me just sort of share my understanding with you. So let me just, so as you can see, this peak, its magnitude and its position depend on the disorder amplitude, basically. Okay, so let's focus on that peak. Why do you have this sort of resonance situation where you have a peak at non-zero noise amplitude, basically? Okay, so that's now I come to my results. I have a couple of minutes. That's okay. So here's the Vichek model results. You start off at time t equal to 0 with a bunch of randomly moving birds, and you finally sort of cluster into these sort of, well, broken up clusters, all moving in the same direction. So this is the angle field of the velocity vector. So because they're all red, you have sort of all the sort of birds moving in one direction. Okay, so that's the steady state of the usual Vichek model. Things are quite different if you put in these scattering obstacles. At zero noise, you no longer have these extended clusters. Basically, what's going on is the following. This is how we understand it. The particle scattering gives rise to correlations. The particle obstacle scattering gives rise to decorrelations. So even if you start off with something like that, you sort of break up into much smaller particle clusters at noise equal to 0. And these, on the average, are being randomly reflected. They don't interact with each other too much. And therefore, you have a sort of relatively lower average velocity out here, as opposed to the Vichek model with no obstacles. Now, as you increase, okay, so again, I should sort of point out that the velocities are coded according to their angles, and you see all sorts of colors. So the velocities of these little mini clusters are pointing in sort of various different directions. As you increase the noise amplitude, these clusters actually become a little larger. And it's sort of easy to understand why they become larger. There's a sort of transverse motion put in by the noise. And as you increase the noise, the size of the cluster goes as a square root of noise if you just do a simple random walk kind of argument, basically. So it goes up as a square root of noise. These larger clusters collide more often. And our understanding is that the peak of, so there's more possibility for correlation. Just 1 minute. There's more possibility for correlations to build up. And you can see, as a matter of fact, again with the color coding, that you have mostly things on the average pointing in one direction. So that's at the peak of the average velocity. And then, of course, as you further build up noise, the clusters break up and sort of randomly move around and so on and so forth, and disorder declines again. So that's the key of our understanding. We believe that the peak occurs when the mean free path between the obstacles is the same as the mean free path of the cluster-cluster collision. Okay, that's our understanding, basically. There's various other ways you could look at it also, but I should probably end because I'm out of time. You can look at the time, you can look at an autocorrelation function, for example. Again, it shows this non-monotonic behavior. The slowest decay of the autocorrelation, this green line, is at the peak of the at this non-zero value of eta, where you have the peak of the order parameter of the system. Okay, you can look at the order parameter as a function of time. Again, you see that sort of this red line is the highest average order parameter, and there are much larger fluctuations because of the fact at eta equal to 0.02, because the clusters are compact and don't really have much sort of collision with each other, and therefore there's no correlations building up. And we've looked at various other quantities, the persistence length, etc. Let me just end, because I have just 10 minutes of my talk. The primary takeaway message is that the Vichek model with scatterers gives maximum order at a non-zero noise strength. For us, this was a little counterintuitive initially, but I think we now have a good understanding on it. We understand how the peak amplitude and the peak position depend on, in particular, on the sort of density of the packing. Okay. At this noise strength, the clusters have fluffed out and their collisions are most frequent at this noise strength, thereby enabling in stronger correlations in the system. And again, that's essentially the same statement as the green one, that the maximum order is associated with the maximum persistence length or the persistence time. So the autocorrelation decays slowest at a non-zero value of noise for the Vic-check model with obstacles. Okay, let me end here.
Maybe quick questions.
Hi, Sanjay. So is there any sort of critical value of this packing fraction above which the peak disappears?
Above which this peak disappears?
Yeah.
So this peak, the point is, at some point, obviously, this curve goes over to this curve. But you
No, but the other direction.
In the other direction. Well, I mean, yeah, it's continuous. It's not a sort of critical value, certainly, as far as we can see. But yeah, sorry, just in the other direction, in the 5-0 going smaller, it's kind of hard to do sort of numerical studies at very small values of 5-0 for obvious reasons here.
This rule that you have for the way the active particles interact with the obstacle it's fine to study it, but actually in many systems you're not likely to see that because these are persistently moving. When they come up against an obstacle, they'll kind of keep their orientation and skirt around, walk around the obstacle. Okay. You see this in these vibrated rod things as well as in some microorganisms. Okay. There are some microorganisms that actually have a reversal rule because it's not a momentum exchange collision. It's a reorientation.
Yeah. Okay.
And so it's not clear what will happen if you made the rule
to that.
If you just made it exclude volume and nothing else.
Yeah. We've taken the simplest limit in some sense. Yeah.
What's the ratio? How does the size of the obstacle compare to the Vic-check interaction radius?
So for now, for these results, the size of the interaction is the same as the Vic-check interaction.
The size of the obstacle and the interaction radius is the same.
It's the same. So if a sort of particle, sort of a cluster goes through this end is still sort of correlated to the cluster at the other end, basically. Yeah. But as I said, in our understanding, there's two limits are much greater than the Vic-check this thing and are comparable and less than the Vic-check interaction radius. Okay, but I've just shown results for R equal to the Vic-check interaction radius.
So let us thank the speaker once again.